Hello friends, today's question. A liquid of density rho is coming out of a hose pipe of a radius with horizontal of a radius. Okay, radius is a, with horizontal speed v, and hits a mesh. 50% of the liquid passes through the mesh unaffected. 25% loses all of its momentum, and 25% comes back with the same speed. The resultant pressure on the mesh will be. So in this case, suppose this is a mesh and the liquid which is coming from the hose pipe, it can be divided into 3 segments. First segment, it passes through the mesh unaffected, which constitute 50%, and the second 25% loses all of its momentum, so it means the 25% is going to lose all of its momentum. Okay, so means all momentum is lost, and finally the last 25% is going to come back. So this is last 25%, it comes back. And we have to find out the resultant pressure on this mesh. So from the figure, this rough figure, we can easily say that the resultant pressure will be dependent upon all these 3 individual components. Okay, let us call this as component 1, component 2, as well as component 3. Okay, so we call this as case 1, case 2, and case 3. So from case 1, we can see that entire 50% passes through the mesh without any creating pressure or force. So there will be no pressure because of the resultant pressure because of this effect. 50%, 25%, and only this 25% is going to affect the resultant pressure. Okay, so we are going to calculate them. So first of all, we can say that the resultant pressure on the mesh (50% of the liquid pass through the mesh unaffected). 50% of liquid pass through the mesh remains unaffected. (25% of liquid loses all its momentum, and the last one is that 25% of liquid is reflected back with the same speed. So like I said, this will be our case 1, case 2, and the last one will be our case 3. First of all, let's find out what will be the total flow rate of this entire liquid or the hose. So we say total flow rate, and let us write it as MR. So total flow rate exiting the hose pipe, total flow rate exiting the hose pipe is equal to MR, and that will be equal to rho A and V, where rho is the density, A is the area of the cross section of the hose pipe, and V is the velocity. You can say rho, density of liquid, A, cross sectional area of hose pipe, which will be equal to pi A square, where A is given as the radius and V is the velocity of liquid. So we can write that our MR will be equal to rho pi A square multiplied by V. So let us solve one by one. So next we are going to find out the forces, and based on the forces we are going to calculate the pressure. So you can say forces acting on the mesh. Forces acting on the mesh. From here we are going to solve it by using two things. First is calculate the resultant pressure. Calculate the resultant pressure, because we know that pressure is equal to force oblique area. And second, we are going to calculate the change in momentum, because force is also related to change in momentum. Calculate change in momentum, because force is rate of change of momentum. Force is rate of change of momentum. Okay, because based on two conditions. First condition was that 25% of momentum is lost, and the second condition is that 20% comes back. So let us solve for case 1. Case 1 says that 50% of liquid pass through unaffected. So it means this portion of liquid, there is no change in velocity, and if there is no change in velocity, there is no change in momentum, or we can say there is no effect of on the pressure on the mesh. So it does not contribute in the calculation of the force. So you can see from here, this portion of liquid does not change its velocity, so does not contribute does not contribute to the force on the mesh. Okay, because the force acting on the mesh will be dependent upon in either of the two options. Okay, it will be either because of the pressure or because of the change in momentum. So as it is passing through unaffected, so there is no effect on the pressure as well as there is no change in velocity, or we can say neither the momentum is changed. Now we come to the case 2. Case 2 means 25% of liquid loses its momentum. Of liquid loses its momentum. So we know that the momentum that will be lost by this portion of the liquid, let us suppose that is given as delta P, and delta P will be equal to m into V. Okay. So we can say the momentum lost by this portion of liquid, this means 25% of the liquid, this portion of liquid, delta P will be equal to m multiplied by V, and it says that only 25% of the momentum is lost. So you can say since 25% of liquid loses its momentum, therefore the flow rate that is associated with it, means 25% of the loss, will be equal to 0.25 mR, where mR is the initial flow rate, okay, of the hose pipe. So we can say that therefore the mass flow rate associated with it, let us suppose that is given as m loss, will be equal to 0.25 multiplied by mR. So from here we can find out the force, and we can say that the force due to this loss in momentum, you can say force due to this loss in momentum, let us suppose that is given as F loss, which will be equal to M loss and multiply by V. So we can write that our F loss will be equal to 0.25 mR multiplied by V, and mR we know is given as rho pi A square multiplied by V. V and V becomes V square. Now we come to the last part, that the case number 3. Case 3, which states that 25% is reflected back with same speed, that is V. So therefore the change in velocity will be equal to when the liquid is reflected back, it undergoes a velocity change, from plus v to minus v. Okay, magnitude will be same but direction will be opposite, so it becomes plus v to minus v. Therefore the change in velocity will be equal to v minus of minus v, that will equal to 2v. So we were able to find out what will be the change in velocity. Now we can calculate the change in momentum. We can say change in momentum delta p will be equal to m multiplied by 2v. And now we can find out the mass flow rate associated with this particular case. So therefore we can say that mass flow rate associated with it, mass flow, FLOW, flow rate associated with it, let us call this as M reflection, which will be equal to 0.25 multiplied by MR. So therefore the force due to reflection, let us call this F reflection, will be equal to, we have M reflection multiplied by V. So we substitute the value M reflection, so we get force reflection will be equal to, M into 2V, my mistake. So we put the value, we get this as 0.25 mr 2v, which becomes 0.5 mr v, and we know mr is our rho pi a square v, so we get F reflection will be equal to 0.5, and this is rho pi a square v square. So now we can find out the total force on the mesh will be equal to summation of all the three cases. In the first case there was no force, so the total force on the mesh will be summation of the force loss and force reflected. So we can say total force on the mesh and that is equal to F total will be equal to F loss plus F reflection. We substitute the value, we get this as 0.25, and that was rho pi a square v square plus 0.5 rho pi a square and v square. And it's almost done. Simple calculation is left now. Therefore, if we add it, we get F total will be equal to 0.75 rho pi a square v square. We are supposed to find out the pressure, so therefore we can say pressure on the mesh, and we know pressure is defined as the force per unit area, so we can say pressure will be equal to F total oblique area. F total is 0.75 rho pi a square v square, and area is our pi a square. So pi a square cancels out. So we get pressure is equal to 0.75 rho v square, and the options that are given to us is in the form of the fraction. It is in the form of the fraction, so we easily can convert it. So there we can say pressure is equal to 3/4 rho v square. So the options available to us, D is the correct option. We can say option D is correct. Okay. So this completes the question. Thank you.